channel, no, bago tayo pumunta sa Weirs. Kasi, well, connected naman sila. Pero ito kasing topic about hydraulic jump is more relative sa open channel. Okay? So this is one of the things that will occur if you are to put humps, parang ganun, no? Or we could say na parang yung mga nilalagay nyo na Weirs that is submerged on a certain ganun, no? On a certain open channel. So mamaya papanood ako sa inyo ng ganun, no, ng tawag dito ng things about hydraulic jump para mas maintindihan natin to. Pero before going towards to hydraulic jump, we should know how, no? How can we know if a certain fluid will be under hydraulic jump? So kailan ba tumatalon ang tubig? Di ba? And this is particularly on a flowing fluid. Hindi siya yung fluid na papatalunin mo na lang bigla-bigla. Kasi 'di ba? One of the things that we need to know under hydraulics is how fluids behave. Lalong-lalo na kapag yun yung mga fluid na ginagamit natin ay yung daily necessities ng isang human being. Of course, it will be the job for us civil engineers in order for us to to deliver hindi lang siya deliver manage the flow of water in and out of a certain community. So yun yung trabaho natin. At maybe one of you in the near future, no? Kasi sa bawat batch na naturuan ko, even our own batch, no? Sa batch namin, meron merong nagtrabaho sa water department. Parang gano'n, no? Water resources. Kasi pag sinabi mong water resources, nandun na lahat Hindi lang siya yung trabaho para sa ano tawag doon? Yung pag-deliver ng water from a certain reservoir towards each of the household sa isang community. Pwede rin yung mga yung mga pag-save ng ating water resources around us na pwede natin gamitin. Ang dami kasing uses ang water di ba? Madami siyang uses. At yun na nga yung pinakakailangan natin ay yung daily necessity natin with them. So, ano din yung behavior na dapat natin malaman when it comes to hydraulic jump, no? Ano yung kailangan nating ma-solve? Kasi 'di ba, if you could remember, ano ulit ang Reynolds number? 'Di ba? When we think of Reynolds number, it will tell us whether the water is laminar or turbulent, 'di ba? Meron din dito sa hydraulic jump. Pero yung term na yun ay hindi naman siya yung kinukuha natin, no? Yun lang yung number na yun, it will tell us whether the fluid is moving too fast or not. Okay? So, ano yun? That would be the fraud number. So, kung may Reynolds number tayo, under hydraulic jump, lalo na sa or hindi lang sa hydraulic jump, no? Under fluid flow sa isang open channel. Okay? Open channel, So, pag sinabing open channel, yung isang surface ay yung isang face ng ating ng water on its cross-section ay open sa atmosphere. So, ito yung fraud number, guys. This is a dimensionless number that describes different flow regimes of open channel flow. So, etong kinukuha natin dito ay yung ratio between yung forces that makes the water flow versus the gravitational forces of the water. Kasi guys, tubig in itself, may bigat yan. Okay? May bigat yan. So kinukuha natin dito ay yung velocity or yung yung ratio between yung bilis or velocity ng isang fluid versus yung kanyang sariling gravitational pull. Okay, downwards, di ba? So, kapag ang fraud number natin ay less than 1, subcritical yung flow, meaning mabagal yung flow ng fluid, hindi siya yung napaka-rumaragasa. Okay? Yung tipong ganun lang, flow lang siya because, di ba, some other bodies of water, kailangan na mag-flow para ma-replenish, kumbaga, ibang parts sa ating mundo. Okay? So, ano naman yung equal to 1? Pag equal to 1, guys, critical flow na siya, which means nandun na siya sa nandun na siya sa boundary between the slow and the too fast type na bilis. Kasi pag greater than 1 na, ayun na, super critical na masyado yung flow, sobrang bilis na nung movement ng ating fluid. Okay? Or nasa critical na siya part. So dito makikita nyo, no, yung amount of discharge habang umaakyat yung depth. Nakikita nyo naman, di ba? Okay? And then this is the part where the energy grade line is. So guys, dito kasi sa may part ng critical stage, baka nagtataka kayo, sir, ang taas ng tubig. Hindi ba mag-flow ng mas mabilis kapag mataas? Take note, guys, if the depth is too high, the Froude number is too low. Kasi at a certain depth, guys, just by having the velocity versus the gravitational forces, kung mataas yung ganon yung tubig, hindi mo napapansin nag-flow ng sobrang bilis yan unless the slope is too high. Kasi di ba, ganon lang naman yung instances na sobrang bilis mag-flow ng water. No, marami rin, maraming ganon, no? Maraming pwedeng ganon diyan. Maraming pwedeng makapagsabi na ang isang body of water mabilis mag-flow. Pero on this particular open channel criteria, one of which would be yung kapag mas maliit, okay, yung depth ng isang open channel, malamang mas mabilis. Or kahit nandun na sa critical stage, kasi mas maganda nasa critical stage yan eh. At a certain depth kasi, it will provide you that maximum flow of discharge. So ito na nga yung nakikita nyo sa right side, that is the, the graph for the depth versus the discharge. So yung iniiwasan dito is kung yung flow ng water ay nandun sa may critical stage na part. Okay? Yun ay kung equal ang velocity at yung gravitational pull or forces ng ating water. So paano kukunin yun? Dalawang equation. May Froude number tayo para rectangular section. That would be velocity over the square root of gravitational force acceleration, okay? Bali 9.81 meters per second squared yan. Tapos yung D ay yung depth ng fluid on that on a particular cross section. Kasi ang hydraulic jump, for example, dalawang magkaibang section yun. May mababa, may mataas. Bakit? Kasi di ba umakyat nga yung tubig, tumalon yung tubig. So aangat yung ganun yan, no? Yung depth of fluid niya dun sa other side, while yung left side mo ay maliit pa rin siya. So pwede mong kunin yung Froude number of a certain flow, depende kung gaano kalalim on that particular section. So pwedeng dalawa ang kunin yung Froude number, or kahit as many as you can, no? Froude number sa isang streamline, or let's just say one open channel streamline. Para sa non-rectangular section naman, yan naman yung Froude number natin. Q squared B over A cubed over times G, no? So yung Q dyan ay yung flow rate, yung B dyan ay yung width ng ating flow. Take note ha, yung width ng flow ay yung width ng water na naka-face sa atmosphere. So kung triangle yan, malamang yung point ng triangle nasa baba. Mamaya pakita ko ano yung B na yan. Tapos yung surface, yun ang gano'n na gagamitin nating B. Okay? Yung gano'n sa surface, na-attach sa surface na width of your cross-section. And then A is area, and G is, yun na nga, same gravitational acceleration. Or you can just use V over square root of G times D, wherein D is the hydraulic depth, at yung hydraulic depth is equal to area over the width of your cross-section. Okay, cross-sectional area yan. So yan ang Froude number. Why? This Froude number will tell us whether a certain open channel flow will have a hydraulic jump or not. So paano nga ba nagkakaroon ng hydraulic jump? So ito yun. So yung hydraulic jump, okay, nangyayari kapag yung Froude number ng isang flow from left side meets a bump, a hump, pwede, or a certain body of water na mas mataas yung Froude number niya. Tama ba? Oh yeah. Kasi the lesser Froude number tayo na. Tama. If the lesser Froude or higher, or is it? No. The higher Froude number meets with a lesser Froude number, there will be hydraulic jump. Okay? So yun, ang nangyayari, because of the rapidly flowing fluid, bigla siyang na-slow down. Ano nangyayari? To convert the energy because of it slowing down, but kasi maalala nyo, nag-Bernoulli equation kayo on a certain streamline, dapat equal ang energy dun. Eh what if naglagay ka nga ng ganun, no? It's a flowing fluid, no? Tapos biglang in-increase yung height on that particular point ng streamline para ma-equate, no, mag-equal yung energy between the 2 points. Since they are of the same streamline, mag-a-adjust yung, di ba, may tatlo tayo sa Bernoulli equation, velocity, the pressure, and the height. So dito, under hydraulic jump, it would be the loss or the energy due to height. Okay? Ang mag-a-adjust, kaya umaakyat yung tubig kapag ganun. Okay? So, if I were to show you a video about hydraulic jump, ito yung isa sa mga nakita ko na maganda with an explanation. No? Tingnan natin kung meron siyang subtitle para mas ganun, mas mainam siyang pakinggan habang babasahin. At meron na nga. Teka lang. Kailangan kong i-ganon yun. Wait lang ha. May ads pa nga. Entire screen ko na lang. Ito.
Objectives of modern infrastructure, from flooding rivers to irrigation canals, stormwater drainage facilities to aqueducts, and even the spillways of dams. So engineers need to be able to predict how water will behave in order to design structures that manage or control. And fluids don't always behave the way you'd expect. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about one of the most interesting phenomena in open channel flow, the hydraulic jump.
Ayan, parang ganyan. Naglalagay sila ng tawag dito. Naglalagay sila ng parang harang. Nagbabago yung gano'n, no? Yung flow ng water on a certain location. Tapos yun na nga, to manage na dapat yung energy. Sige, share lang muna.
But unlike rockets, you probably already have some intuitions about how water flows. The study of how water with a free surface behaves, that is not confined within a pipe, is known as open channel hydraulics. This field is especially useful in civil engineering, where structures can't usually be tested at scale. We can't build a dam, cause a flood to see how well the spillway works, and then rebuild it if the performance isn't up to standards. Instead, engineers need to be able to predict how well hydraulic structures will perform before they're ever constructed. This is the definition of engineering. To take theoretical knowledge of science and physics, in this case fluid dynamics, and apply that information to make decisions about the real world. One of the most important parameters in fluid dynamics is velocity, or how quickly the water flows. Sometimes velocity is a good thing, like when you're trying to move a lot of water quickly, for example in a flood. Sometimes velocity is a bad thing, like if you're trying to avoid erosion. Either way, it's almost always a key criterion when designing hydraulic structures. But the velocity of flow isn't the only velocity that's important in fluid dynamics. We also care about the velocity of waves, or how quickly pressure disturbances in a fluid can travel. If the flow velocity is exactly equal to the wave speed, we call the flow critical. But it's more likely that these two velocities are different. Slow, tranquil flow conditions are called subcritical. In this case, the wave speed is faster than the flow velocity. You can see that the waves can travel against the flow direction. Because of this, the depth is controlled by downstream conditions. You can see that anything I do upstream isn't changing the depth of this flow. Fast-moving flow is called supercritical. In this case, the flow velocity is faster than the wave speed. You can see that the waves aren't able to propagate upstream. Supercritical flow is controlled on the upstream side. So nothing I do downstream affects the depth of the supercritical flow above. A flow profile can naturally transition from subcritical to supercritical. That is, from slow to fast. For example, if a channel changes to a steeper slope or a cliff, many types of flow measurement devices rely on forcing a flow to transition from sub to supercritical because there will be a unique relationship between the flow rate and the depth for a given geometry. Maybe we'll talk more about flow measurement in a future video. But when flow transitions the other direction, when a fast-moving supercritical flow transitions to a more tranquil subcritical condition, something much more interesting happens: a hydraulic jump. The classic demonstration of a hydraulic jump can be seen at the bottom of your sink. Open the faucet and watch how the flow behaves. You can see the fast-moving flow right into the stream.
Teka lang, set ko lang yun ha.
The sink and the abrupt transition of the hydraulic jump to a slower moving flow. But the sink demo isn't the best example because it happens due to surface tension, not ground. Plus it's kind of boring. So I built this flume in my garage to give you a better look at the hydraulics. If I open the upstream gate by just a little bit, I can create supercritical flow in the flume. Now, if I obstruct the area downstream, I can force the flow to transition into subcritical. Right where the flow transitions, you can clearly see the hydraulic jump. This phenomenon happens naturally in certain locations. Steep mountain streams often have supercritical flow, crashing into rocks and changing slopes, creating whitewater and turbulence, and the occasional hydraulic jump. Also, a tidal bore occurs when an incoming tide forms a wave that travels upstream against a river. These events only occur in a few places across the world, but it's fascinating if you get to see it in person. In many cases, the bore travels as a moving hydraulic jump, similar to what you see here in my flume. But jumps aren't just natural phenomena. They're important in hydraulic structures as well, especially for energy dissipation. A major part of the job of a civil engineer working in the field of hydraulics is designing against erosion from the flow of water. When we try to control the flow of water, that often leads to the potential of having fast-moving erosive conditions. For example, when we put water in a culvert rather than allowing it to flow over a roadway, it can pick up speed in the pipe. When we line a ditch or creek with concrete, the smoothness speeds up the flow compared to natural conditions. And when we make releases from a reservoir behind a dam into a spillway, the water can come roaring down at extremely high velocities. This supercritical flow can cause erosion and eventually lead to failure of the structure. So most hydraulic structures will be equipped with some form of energy dissipator on the downstream end to reduce the velocity of flow and protect against erosion. There are all kinds of hydraulic energy dissipators, but for large structures like spillways, the most common types rely on the formation of a hydraulic jump. Because a hydraulic jump causes so much turbulence, it's able to effectively dissipate hydraulic energy as heat. So many energy dissipators, also called stilling basins, are designed to force a hydraulic jump to occur. There are many types of stilling basins, but most use different combinations of blocks, insills, and overall geometry to control how the hydraulic jump forms. The turbulence stays within the stilling basin with the objective of having smooth, tranquil, subcritical flow leaving downstream, minimizing the potential for erosion, which would otherwise threaten the integrity of the structure. Hydraulic jumps don't just serve utilitarian purposes. Recreational whitewater courses can be found across the world, and many of these courses make use of hydraulic jumps as artificial rapids. In fact, many kayak parks started out as obsolete dams in need of removal. A perfect opportunity for replacement was something more beneficial to the community and the environment. Freestyle kayaking, also known as playboating, involves performing tricks in a single spot. Playboaters use natural and artificial hydraulic jumps to stay in one spot. I've never tried this myself, but it looks like a lot of fun. Next time you see water flowing in an open channel, try to identify if it's sub or supercritical, and keep your eye out for hydraulic jumps. Thanks to NordVPN for sponsoring this video.
So yun guys, no? That's how you try to relate hydraulic jump with what we have around us in our in the real world, di ba? It shows naman no yung tawag dito na ginagamit itong hydraulic jump for a certain purpose, like one, yung erosion. Pwede nga rin na gawin itong CE projects nyo later on kung may CE projects pa rin kayo for a certain part of our community kung sakali lang to answer problems around us. Kasi di ba, saan ba nagkakaroon ng mga soil erosions dito? And what do we do in order for us to reduce the velocity. Isa yun, yung ginagamit natin ay yung nakikita nyo na hexapads, di ba, na nasabi ko last time. So that is one possible way to reduce man lang the velocity of the water kasi nga napakadelikado ng tubig. Kahit sa anong gano'n, kahit na anong situations. Sabi ko nga sa inyo, meron pa yung tubig na gano'n, no? Or yung fluid na ginagamit nila para mag-cut ng bakal, di ba? So, ganun siya kadelikado. So, kailan ulit nangyayari ang hydraulic jump? Hindi lang naglagay siya ng harang kaya nagkaroon ng hydraulic jump, no? Pero that's one way din kasi. Doon siya nagkakaroon ng ganun ng parang ramp para mag-flow siya paangat, no? Magkaroon ng variations with the flow, not just flowing on a certain open channel, din bigla na mag-jump on that harang nga na nilagay niya. Because of gano'n na rin, no, biglang in-slow down yung fast-moving water. That's the idea there. Bigla mong pinatigil kaya umangat siya to balance out the energy. Kasi hindi mo pwedeng gano'n yun eh. Hindi mo pwedeng ang energy is not destroyed too fast. It's being transformed, di ba? Hindi pwedeng ma-destroy ang energy. It will be transformed to another. So, yun na nga, yung transformation na naganap ay to equate the energy between the fast-moving and the slow-moving part. So, mangyayari doon, yung H, no? Diba? V squared over 2G plus yung pressure over gamma plus yung Z, diba? So, yung Z yung nag-adjust para ganun, no? Yung energy ay hindi ma-destroy. Well, hindi naman talaga ma-destroy, no? Pero may mag-a-adjust talaga dun sa energy equation mo since we're dealing with flowing water. Okay? So yun, kino-convert yung initial kinetic energy ng flow to potential energy. Yan na yung Z, di ba? Tapos yung ibang energy, irreversibly naman na siya lost due to the movement, no? Pero tinransform niya into turbulence o to heat. Okay? So that is with the hydraulic jump, abruptly changing the flow property of a fast-moving fluid, and then yun na nga, it will create that jump due to that. Okay? So, ito yung explanation dun sa sinabi ko kanina kapag initial speed ng fluid below the critical speed, hindi hindi siya magkakaroon ng jump kahit harangin mo. 'Di ba? Pinakita naman kanina, even though hinaharang niya, hindi nagkakaroon ng changes in the flow. Meron yung mga ganun, no? Lalo na kapag yung flow mo naman sa umpisa is, alam mo yun, yung tranquil. 'Di ba? Sa front number, balikan natin. So kapag yung flow mo ay subcritical or yun na nga, slow pa, tapos bigla mong haharangin for you to apply hydraulic jump, hindi pwede mangyari yun. It only happens when, yun na nga, sa mga supercritical flows. Okay? Then, bigla mo siyang abruptly transition to slow to, to equate the energies for the boat, yung potential energy yung magbabago. So, dito yung explanation nito. Meron tayo nito sa lab sa school. Pero ang kinocompute lang naman natin dun is the same with what we're computing on our lessons. So, ito na nga yung equation natin. Ito yung property ng isang hydraulic jump. No? It should show like this one. So, ang idea behind dito ay kinukuha yung stress or yung force dito sa may initial depth niya versus dito sa may final depth niya. So may force kasi dito that will try to adjust this flow from this lower portion to this upper portion. So yun nga yung change in forces from this one to this one. So yan. Equate it to yung rho QV na kinukuha natin as a equation for force. Okay? Force equation yan. Then the force for the point 1 or the force in this second point minus yung force dun sa F1 dito sa first point natin. Pwede natin i-equate with this, knowing that rho or density is the same as unit weight over gravity. And then with this, guys, we can relate or mahabang derivation to, pwede nyo lang naman i-search or kapag sa akin kasi is iba yung nakuha kong equation. Yung for any sections yung nakuha ko eh. Pero for triangular kasi, substitute nyo na lang dito. So, these equations will lead to eto. Nakikita nyo sa ilalim. So, itong Q na maliit, iba sa Q na malaki. Okay? So, yung Q na maliit, that is unit flow. That is the unit, that is the flow rate per unit meter of a width. Kaya yung Q na maliit is equal to Q na malaki divided by yung B, which is yung, gano'n, no? Yung width ng cross-section. So, for rectangle, yung gano'n niya, no? Yung width niya mismo na letter B sa baba. Diba? Tapos yung D, yung depth. So, yun yung gano'n, no? Yung Q na maliit dyan. And then yung G dito is the acceleration due to gravity. Yung D1 ay yung depth sa my first point. Then D2 is depth sa my upper point. So for any sections, ito yung magpapakita. So yung A dyan, yung area, no? So yung area para sa rectangular section kasi ay B times D1, you know, or B times D2. Hindi nagbabago yung ganun guys, no? Yung B all throughout the flow. Hindi nagbabago yun dito. Kapag rectangular. For any sections kasi there are changes, no? Pero nasa examples naman natin yan and I will show you that later. Nadoble ko tuloy ito. So yung unit flow guys, yung Q na maliit is equal to VD or we could say na Q over V siya. Or yung flow rate natin divided by yung width ng ating channel. So it's in cubic meters per second per meter. Yan siya. This is for rectangular sections only kasi yun yung ginagamit nating equation dito. For any sections, hindi naman natin kailangan si maliit na Q. Okay. So ito yung classification of hydraulic jumps. Yan na yung pag fraud number mo ay less than 1. So malamang imposible mangyari yung jump kasi nga 'di ba yung fraud number between the 0.1 and 0.2 hindi siya nag-transition from subcritical from supercritical to subcritical, no? Same amount of fraud number lang. But if the fraud number is 1 to 1.7, medyo magkakaroon na, no? Na malit lang. Para naman sa 1.7 to 2.5, tapos yung changes ng hydraulic jump is ganun, no? Or yung taas or the ratio between the lower or the higher and the lower ay 2 weak masyado pa yung jump dito, then papangat na papangat up until yung fraud number mo is greater than 9, tapos yung ratio between the higher depth versus the lower depth is 12, sobrang lakas na nung hydraulic jump niya. Okay, so you can use this as a relationship later on kung kailangan nyo ng idea behind our hydraulic jumps. And dito tayo. The depth of flow before the hydraulic jump was observed 860 mm. So before magkaroon ng hydraulic jump, 0.86 meters yung depth. Yung flow rate niya 25 cubic meters per second, mabilis na yan. And the flow width of the rectangular channel is 3 meters. Now, determine the fraud number before the jump, determine the depth of flow after the jump, determine the fraud number after the jump. So, ano muna yung fraud number before the jump? So, meron tayong Q, pwede natin makuha yung velocity by dividing Q with area. Diba? So, yun yung ginawa ko sa V dito sa letter A, no? 25 cubic meters per second divided by yung area ng rectangular channel dun sa bago pa nag-hydraulic jump. So, rectangular, 3 meters yung width, yung letter B mo ay 3 meters, tapos yung depth mo sa may una, depth 1 is 0.86 meters. Ayan. Divided by square root of yung gravitational acceleration times yung depth dun sa una. Makuha natin na yung fraud number is 3.34, which is telling us that at the start, before the hydraulic jump occurs, the flow is supercritical. So, determine the depth of flow after the jump naman. So, yung, wait, lang tumatawag si Ma'am Pyring. Okay na guys, that's with regards to defense kasi may mga masters na magdi-defend and we were asked to ganong panel mamaya. Okay. Continue natin. So yung depth of flow after the job using yung formula kanina. Yung small q, that is yung big Q divided by yung B. So yun na yung nandito na 25 cubic meters per second divided by 3 meters. Squared over yung G natin na 9.81 meters per second squared and yung D 1.86. So D2, hindi pa natin alam yan. Shift solve na lang natin yan mamaya. Tapos the rest. Then, makukuha nyo, shift solve natin, D2 is 3.65 meters. So from 0.86 meters, umakyat siya ng 3 meters. No? Ganun kataas na flow or na jump. So kunin natin yung Frog number dun sa may after ng hydraulic jump at makikita natin na 0.382 na lang yung, di ba? Yung Frog number, meaning it's subcritical, mabagal na yung ganun, no, movement ng ating flowing water dun. So ganun lang naman ang hydraulic jump, hindi siya ganun kahirap. Pangalawa natin ay yung nga rectangular channel na naman of depth 30 centimeters. What is the Frog number after the jump? Yun lang yung tinanong. So ito, simple lang. Kunin mo lang, kinuha ko na lang muna yung velocity, hindi ko diniretso katulad yung ginawa ko kanina. So kunin yung velocity divided by the square root of yung acceleration due to gravity, yung 0.3 na depth. So yan, kuha natin yung Frog number for before the jump, 3.53. Then solving for the depth of the after the jump, makukuha natin siya as 1.36. So look at that. From 0.3 meters, nag-jump siya 1 meter high at 1.36 meters. Kunin nyo na yung velocity at the second. Pwede lang din gamit yung depth number 2 na 1.36. It will show you that the velocity reduced. Naging 1.34 meters per second from 6.06 meters per second. And then, kunin nyo man yung fraud number niya, kasi yun naman yung tinatanong, eto na yung answer. Okay? And lastly, ito yung triangular na binabanggit ko. No? So sinabi dito, yung gano'n na channel natin 90 degrees, no? Na triangular. So even though yung nagkaroon ng hydraulic jump, it should still give us a cross-section of a triangle. So ganito lang naman siya. Ang hinahanap dito, iba. Ang hinahanap dito ay yung discharge. So ito yung clear idea before. Tama? Diyan nakuha yung equation ng hydraulic jump, guys. Yung force is equal to rho QV. Okay? So, next is kinuha naman natin yung gano'n natin, no? Equation niya by having the point 2 where the hydraulic jump at the second point of cross-section is being placed and at point 1 dun sa start before the hydraulic jump. So, kunin muna natin yung force 1. So, the force 1 is, di ba, paano nga ba kunin yung force on a certain cross-section? Yung natutunan natin sa hydrostatic pressure. And that is gamma H times area. Di ba? Gamma H times area, yun yung force sa isang cross-section ng isang streamline. So, yun, gamma ng water times height. That would be, take note yung height last time, kapag ang gate mo ay rectangular, malamang ang gagamitin mo ay yung gano'n, no, over 2. Dito, gagamitin natin yung over 3 since it's a triangular form. Okay? Diretso na kasi to, guys, ha? Maybe you're wondering. Diretso na kasi to. Diniretso ko na to. Times 0.152 square meters. Kaya, ayan na yung force number 1 natin. Then, force number 2, same scenario. Instead, ang gamitin nating height would be yung divided by 3 na agad. Diretso na kasi to. Pero kung trip nyo, unahin mo na yung pressure, okay lang din. Okay? So that's force 1 muna and then force 2. And then, after natin makuha yung force 1 at force 2, yung velocity 1, velocity 2 naman na. So for the velocity 1, edi yung unknown na Q divided by yung cross-sectional area dun sa may before the hydraulic jump. Then yung V2 naman is yung flow rate since nasa isang streamline sila, di ba? Hindi naman sila nag-branch out. Then yung Q for the first point is equal to the Q on the second point. No? So V2 would be Q over yung cross-sectional area nung ating cross-section na triangle. So that is 1.59 square meters. So 1/2 base times height, no? Nakuha yung mga yan. So going back to the equation na initial kanina, substitute mo na yung force 1 minus force 2 equals yung unit weight ng water, which is 9.81 kilonewtons per cubic meter, times yung flow rate Q, divided by yung gravitational acceleration, which is coincidentally the same as 9.81 meters per second squared, times yung velocity 2, velocity 1 pala, minus velocity 2. And the Q is now 1.02. So, yan yung mga instances na hindi natin gagamitin yung direct formula for our hydraulic jump. But rather, we use yung, yung concept behind on how it occurred to that value. So, doon lang din kasi galing yung equations ng hydraulic jump na ginagamit natin. So, yun lang naman ang hydraulic jump. No? So, isa pang pwedeng tanong dito, guys, what if tatanungin kung ilan yung energy that was lost? Okay? So, kunin natin yung energy at point 2, tapos yung energy at point 1. Okay? Then, i-minus mo sila. So, pwede rin kasi nating alamin yun. How much energy was lost? Minus lang. Kunin nyo lang yung energy. So, ano yung mga energy pagdating dito sa point 1 and point 2 natin? So, ano ba yung equations natin? Wala naman tayong head loss dito. Bakit? Hindi naman siya closed pipe. Pero pwedeng may friction dito, guys. But without considering the friction, head loss, meron tayong velocity, v squared over 2g. Wala tayong pressure since open siya sa atmosphere. Tapos meron tayong z. So dalawa lang. It would be the head loss daw. It would be the energy due to kinetic, v squared over 2g, and the energy due to potential, na z. Yun lang yung energy na meron dito. So guys, anong relationship nito dun sa topic natin na open channel? So guys, yung open channel na sinosolve natin before, na diniscuss ko, those are for uniform flow. Ano ulit ang uniform flow? Velocity is equal all throughout, tama? How about this guy? Nung nangyari na ang hydraulic jump, under na siya sa non-uniform flow. What if, yun na nga, di ba? Hindi equal yung velocity between an open channel. Hindi papasok yung hydraulic jump topic. Even the Froude number. Pero pwede rin, no? Even though dapat ganun eh. May nangyaring jump eh, para masabi mong non-uniform yung flow. Kasi kung equal lang din naman pala yung ganun, all throughout, hindi, di ba? Edi uniform flow na yun. Okay? So that is Froude number and hydraulic jump. No, simple formulas lang siya. Yan, no? Simple formulas lang. Then next is Weirs now. Isip ko na tao. Bago boses ko. How about Weirs naman tayo? So let's discuss about Weirs naman. So ito is ganun, no, in relation to open channel. Inuna ko kasi to na in-upload kesa dun sa isa para lang mapakita ko yung relationship between open channel and weir. Pero dapat mauna yung hydraulic jump, no? Hydraulic jump muna kasi property siya ng open channel. It may occur if the open channel is non-uniform. So mauna dapat yung concept of hydraulic jump versus yung weirs. So weirs are like this, no? Lalagay ka ng it's a hydraulic structure. Ilalagay mo sa isang flowing na fluid, which is yun nga, normal to the direction of the flow. So ginagamit to para makontrol yung flow ng water, no, from a fast to slow din. Pwede yun, or yung tawag dito, slow to fast. And measurement na rin kung tutusin. Yung nakikita nyo sa left, guys, pansin nyo yung flow ng water from a larger area, pinapaliit nila yung cross-section, di ba? So what happens there is, it will, of course, move faster than before. While yung nakikita nyo sa right, sa tingin ko, mabilis na moving yung left. And then, pinapabagal nung weir para pag flow pababa, hindi bumagal na yung movement niya. So, isa sa mga reason, sabi nga dun sa ganun kanina, yung hydraulic jump, di ba? May hydraulic jump na nga dito sa nakikita nyo ngayon eh. Yung pinapabagal niya yung flow kasi delikado ang tubig. Kaya niyang ganun, no? Mahukay yung lupa sa gilid-gilid niya at baka mas lumaki yung body of water mo, di ba? I remember similar thing happened dun sa may Kataggaman, no? Yung hindi pa na-build yung ganun, yung anong tawag na ba nun? Yung nilalagay nila sa gilid ng riverside. Nalimutan ko. Kasi ako nag-work dun eh. So yun, that is concrete kasi para kung sakali man na mag-flow yung water dun, reduce man lang yung velocity and of course hindi niya mas-scar yung lupa kasi 'di ba ang lakas naman ng tubig na flowing water, lakas naman ng flowing water na ganun natin sa river natin kung kaya niyang hukayin ng concrete. Wala pa naman ako nababalitaan ganun. river flow na nanguhukay ng concrete. Lupa, meron. Okay? So ito yung difference na pinakita ko na sa inyo last time. Pag open channel siya, open lang siya with respect to the container. Pag where nilagyan siya ng something to to control the flow, pwedeng pabilisin o pabagalin yung gagawin. So yan din yung nilagay kanina guys para, diba? Yan yung nilagay kanina para magkaroon ng hydraulic jump para bumagal yung flow ng water. Ito yung section ng isang sharp-crested weir. Mamaya yung hindi sharp, no? So, pag sharp-crested weir kasi ganito yung maging itsura niya. Nagkakaroon siya ng parang arc, no? Due to that sharp edge dun sa may weir plate, nagkakaroon ng arc na ganyan. We have the upper nap and lower nap ng ating fluid. Ito yung types ng weir according to crest. So, meron tayong sharp-crested. Sabi ko nga kanina, yung matulis yung dulo niya. Rectangular is possible. Meron tayong suppressed at saka contracted. So, pag suppressed kasi guys, yung L natin and W are equal. So, yung L dyan guys ay yung size ng weir. While yung W, yun yung size ng channel. Okay? So, pag equal yung L at W, suppress ang tawag doon. Suppress na rectangular, sharp-crested weir. Tapos kapag hindi sila equal, contracted ang tawag doon. May dalawa pa tayo under contracted weir. May one-end contraction at may two-end contraction tayo. May formula para sa dalawang yan. Meron din tayong triangular weir at meron tayong trapezoidal weir. So, yun. Under sharp-crested yan. No? Pag broad-crested naman, ganito yung ganun yan, no? Ganito yung behavior niya. Broad-crested. Kanina matulis, ngayon broad na, no? Yung kanyang ganun. Nilagay na harang or weir. Meron tayong rounded upstream at may square upstream tayo. So yung dalawa nating weir according to crest, no? Sharp-crested or broad-crested. Ito yung equation, guys. Ito yung memorize na equation dito, yung nasa baba. Yung Q is equal to CW LH raised to 3 halves. Pinakita lang dito yung equation, no? Ito yung nasa left side, yan talaga yung actual discharge. Tapos ni-reduce na lang yung info. So dito, ginawa na yung CW, constant for wear, is 2/3 of the constant C Chezi, okay? Times 2G. Square root of 2G, 2 times gravitational acceleration. So, yun, that is kapag may given na velocity of approach. Okay, so yung velocity of approach is yung may initial velocity ang ating fluid coming to the weir. So, kung may velocity of approach na given, edi yan. Okay? Pero pag walang velocity of approach, okay, ang equation natin napakasimpleng ganito lang. Or we can reduce pa ito, 2/3 C square root of 2G, maging CW na lang siya. Or yung wear coefficient. Or wear constant, no? Pero, should I say that as constant? Hindi siya constant eh. Kasi square root of 2G. Hindi siya constant actually. So, dapat wear coefficient lang. Mali pala na sinabi kong constant siya. May unit yan. And then L is the wear length, H is the overflowing head. So guys, yung H dyan, hindi yung depth ng fluid. Yan ay yung layo ng water surface sa taas ng weir. Yun yung H natin. Ito naman yung standard weir formulas. So, with one, ang tawag dito, hydraulic na professor, or let's just say na doctor, na kumuha siya ng gano'n ng idea ng values ng wear coefficient. At yun na nga. Through Francis formula, nakuha niya na yung CW pwede nating take as 1.844 SI units, while yung isa naman ay 3.33 para sa English units. So, nakikita nyo sa baba, yung contracted wear naman. No? What if yung L natin ay 1N contraction, tapos yung isa 2N contraction naman siya. So, ganun lang. Pag 1N contraction, your N or the number of contraction is equal to 1. Malamang kasi 1 lang naman, di ba? As 2N contraction, the number of contraction is 2. So, N will be 2. Then, the formula here, kukunin natin guys kasi yung LC. Yan yung kukunin natin na value para dun sa equation natin ng wear. No? So, LC is equal to yung L na length or yun na nga yung original na length ng ating wear minus 0.1 times yung number of contraction times yung overflow head. And that is now your LC, which is gagamitin mo sa equations. Mamaya. What if triangular wear naman siya, magbabago, no? Instead of 2/3, ang ginamit sa triangular is 8/15, which is nakikita nyo ngayon. So, those are, guys, no? Maybe you're wondering, sir, paano na-derive yung mga iba dyan? Yung ibang values dyan, guys, they're all derived empirical. So, pag sinabing empirical yung derivation, ibig sabihin, galing sa experiments. Yun yung mga, alangan naman, maganong mo, no? Mapalab mo sila with the use of just theories, no? Gumamit ng ganun dyan, ng experiments, kaya may mga values tayo dyan, no? So, wala tayong magagawa. Hindi natin kayang i-derive yan once na ganun tayo nakalimutan natin, we need to memorize. So, ang ginawa naman dito, ang wear coefficient naman ay 8/15, c square root of 2j. So, ang standard equation natin para sa 90-degree na wear, so pag sinabing 90 degrees to guys, pwede nyo nang gamitin to. 1.4 h raised to 5 halves para sa English, metric unit, 2.5 h raised to 5 halves para sa English unit. Pero pag hindi 90 degrees yan, kailangan tong formula na to. And then lastly for trapezoidal. So sa trapezoidal, ang gagawin nyo lang dyan guys, di ba? Pag hinati yung trapezoid, para lang siyang isang rectangle na hinaluan ng dalawang triangle sa gilid. Pero yung dalawang triangle sa gilid, pwede nyo pang i-combine para isang triangle na lang. Tama? Di ba? Pag hinati mo ang isang trapezoid, yes yun? Okay. So, pag hinati mo ang isang trapezoid, di ba? Mahati mo siya na isang rectangle sa gitna, isang triangle sa left, isang triangle sa right. Tama? So, ang gagawin dito guys, instead of 3, i-combine nyo yung 90-degree triangle sa left sa 90-degree triangle sa right para isang triangle na lang. Pagdikitin mo sila. Tama? So, that is your trapezoidal wear. You just combine the Q4 rectangular sa Q ng triangular. So, yun. Yun ang kita nyo yung equation sa taas. Yan na yung ganun na equation niya. So, yung CW1, yan yung wear coefficient para sa rectangular. And ito is CW2, wear coefficient para sa triangular. Take note, pagkaiba sila. Kaya nilagay kong 1 at 2 yan. So, under trapezoidal wear, meron tayong specially called na wear. Yung sinasabi nilang Cipolleti wear. So, yung Cipolleti wear, yung side slopes niya is 1:4. 1 horizontal, 4 vertical. Okay? So, ito naman yung equations niya. So, pag sinabing Cipolleti wear, pwede nyo gamitin yan. Nasabi na agad yung side slopes. So, examples tayo. Ayan naman, rectangular channel. 1.8 meters wide. So, yan yung B niya. Tapos, convey sa water at depth of 1.2. So, what's the velocity of the flow kapag ang slope mo ay 0.002, tapos yung N mo ay 0.012. So, yung N, guys, yan yung Manning's, no? Manning's N. Meron pa rin kasi tayong, ganun dito, no? Idea behind those different, ano tawag din? Different na mga scientists. So, pupunta pa rin dito yung natutunan natin sa open channel. Yeah? Nasa open channel to na-derive. Itong mga to, yung Manning's, Chezzi's, Cutters, di ba? So, pwede pa silang include dito. So, dito ginamit si Mannings. So, 1 over n, r raised to 2/3, s raised to 1/2. Kunin daw yung velocity ng flow. Substitute nyo lang yung mga values dyan. Wherein r, ano ulit ang r? R is your hydraulic radius. So, A over P siya. Wherein A is area and of the cross-section and P is the wetted perimeter. Yung basa lang na part na basa lang na part sa perimeter. Okay? So, yun. And then, yung S natin ay yung slope. Yung slope, guys, na titingnan mo sa gilid, no? Okay? Titingnan mo yung side view ng flow and then makikita mo yung slope niya. Usually, maliit lang yan, guys. Hindi mo kasi napapansin yan. Parang ganun. Diba? Pansin nyo ba sa paligid nyo sa ganun, sa streets? Hindi ba siya slope? Actually, guys, slope yan. Maliit lang. Kasi kung hindi moving yan, guys, hindi, ibig sabihin, hindi magfo-flow yung mga tubig sa kanal nyo papalabas. So, dapat flowing yan. Teka lang, ha? Sorry guys, I'm not feeling that well kasi no. Ah, ano ko may sipon ako eh. Anyway. Saan na ba ako? Okay. So, you can read this parts na lang, pero I should explain some kasi may mga hindi tayo na ganun siguro dito na nalagyan ng mga units kasing lalaki or ang haba ng mga formulas ng iba dito. So, sir, question. Is this something that we should memorize for the board exam? I think yes. Why? At some point kasi guys, hindi, may mga times na hindi sila nagbibigay ng formula. Lalong-lalo na sa mga hydrogeo. Hydrogeo talaga, no? Pinaka-notorious sila na hindi magbigay ng formula. Kakailanganin mong gamitin siya para masagutan. So that would be a problem for you if it's just the formula na hindi mo alam, pero yung process niya sobrang dali. Diba? Sayang naman yung puntos sana doon. So I suggest later on when you review, doon kayo mag-focus sa hydrogeo ng formulas. Kasi ang dami yung i-memorize doon. Okay, so ito lang naman ay para sa pagkuha ng velocity ng flow kapag ang slope mo ay given and yung Manning's N ang nilagay na coefficient for friction. How about yung discharge if the channel may slope siya na 0.1 degrees? Take note pag 0.1 degrees yan, that's not the actual slope. Degree pa lang yan, okay? So hanapin natin what if point or a degree is given for us. So pag degree yung binigay guys, ganito lang naman, no? Instead of applying 0.1 as the value, kunin nyo na lang yung tangent of 0.1. Okay? So ano ba yung tangent, di ba? That's the ratio between the rise over the run. Okay? So yun lang naman, kapag angle yung binigay guys, just place it, your S as tangent of 0.1. Okay? So, under cutter C kasi, N pa rin naman yung binibigay, no? Pero specifically, sinabi dun na malamang cutter's formula yung gagamitin. Manning's N yung coefficient. So, makuha mo dyan yung Chezis C. So, ito yung C coefficient ni Chezi para makuha nyo yung C squared of RS natin. And this time, that would be the discharge for the channel. Kaya multiply mo ng area yung C times square root of RS. Ano lang, velocity times area. And then, para sa velocity of flow natin, pwede natin gamitin yung kay ganun, no? Yung kay, kanina na nga ba to? Ito yung pinaka, ganun concept ng F, di ba? Kung paano na-derive. Nakalimutan ko kaninong C ito. So, square root of 8G over F naman. So, ang ginamit dito ay yung friction factor F instead of yung N, di ba? Yung F ang ginamit natin. So, that is 8 times yung acceleration due to gravity divided by yung F friction factor of 0.02. Kuha natin yung Chezis coefficient na 62.64. Then, substitute it, applying it with the equation for velocity of C squared of RS. Substitute nyo lang lahat dyan. Makukuha nyo na yung ating velocity of 0.729 meters per second. Ganun lang naman yung idea behind dito. Ang nagpapatagal actually ay yung pag-alala mo ng equation. Pero yung transition naman ng ating solution to solution, hindi naman siya kahirapan. Basta yung mainly nang ginagamit dito, yung idea behind the flow rate is equal to area times velocity. Apart from that, yung isa pang formula para sa flow rate ng isang para sa velocity, di ba, ng isang open channel, that is in relation with Chezis C coefficient with the hydraulic radius and the slope. Sila lang yung mga kailangan nyo dito i-memorize. Okay? Suppress triangle sharp crested weir. Okay, suppress na rectangular. So, ayan yung equation niya, di ba? Yung 2/3 C square root of 2G L times H raised to 3 halves, di ba? Pero pwede rin natin kunin siya in terms of using Francis formula. Lalong-lalo na, okay, kapag walang binigay na C. So, yung Francis formula, guys, yung wear coefficient na yung dating binigay. Okay? Hindi yung C, it's the CW. Kaya importanteng alamin niyo yung difference between the C constant ng Chezi versus CW, which is yung wear coefficient. Okay? So in this case, since gagamitin natin Francis formula, kasi no choice ka eh. Even the board exam, guys, wala kang mahanap na value ng Chesis C. Diba? Eh, rectangular naman siya. Suppress pa. So, ano gagamitin mo? Alalahanin mo na lang, no, na may empirical value tayo ni Francis. Francis formula of CW 1.84. Pwede nyo gamitin yan. Kapag, kasi ba, hindi mo masasolve to. Kulang yung given. So, you can use na nga, sabi ko nga, itong values na nandito. And makukuha nyo na yung flow rate of 0.082 cubic meters per second. Okay? Ganun lang naman ka, ganito lang kasimple. Tapos, alahanin nyo, meron tayong criteria na what if my velocity of approach? Balik lang sa original formula niya. Ang nangyari lang naman sa original formula, guys, itong VA over 2G na add sa head and then minus din siya dito. Kasi pag nag-zero yung velocity of approach, babalik lang siya sa h raised to 3 halves. Wala na. Di ba? So, nangyari dito, pag 0 to, babalik lang siyang h raised to 3 halves, babalik sa formula ng CW L h raised to 3 halves. Okay? Pero pag meron, ipa-plus nyo siya and then minus dito. So, ito na yung panibagong flow rate mo for a given velocity of approach. Then, meron tayong rectangular, sharp-breasted weir. May dalawang contraction. So, ito, may contraction tayo. So, guys, Francis formula pa rin yung ginamit dito since walang binigay na C. No? Defaultly do that. Kasi empirical formula na siya that is widely accepted. That's why you can use that. No? So, instead of using L, guys, since may contraction tayo, ang gamitin nyo sa formula ng Q, that should be LC na. Okay? So, isasolve nyo pa yung LC. Ano ulit yung formula ng LC for a double contraction? So, L minus 0.1, yung N value mo, 2. Kasi double contraction nga. And then, yung H niya is 0.3. Take note, yung 0.3 na yan ay yung height ng fluid doon sa kabila. Tapos, hanggang dun sa taas ng ating weir. Okay, hanggang sa taas ng weir dun sa may contraction part. Eh, hindi siya sa total depth, May mga nalilito dito nun eh. Akala nila yung height ay yung total na lalim ng fluid sa loob. Well, in fact, it should only be this one. Since we're dealing with weirs, di dapat yung mga ganun lang, no, info about the weirs lang din yung gagamitin natin. So, LC, 0.6 meters minus 0.1 times yung number of contraction, 2 times yung H natin na 0.3 meters, makukuha mo na yung LC na gagamitin ay 0.54. Ayan na. Solve nyo na, 1.84 using Francis formula. Kuha na natin yung flow rate ng isang sharp-breasted weir. Neglecting the velocity of approach. Ito naman pag triangular yung weir, no? Simple lang naman pag binigay na yung wear coefficient. So don't worry. 2.1 wear coefficient. So lagyan mo na lang agad dun. Wag kayong malilito sa C tsaka wear coefficient. May mga gumagawa kasi niyan na nalilito, no? They input it in C rather than in CW. So ito, direct formula na lang. Since 60 degrees ito, hindi natin gagamitin yung gano'n, no? Yung formula na isa na default. So ito na lang gagamitin natin. Okay? And yung flow rate. Then lastly, ito, trapezoidal. So ang gagawin natin, hatiin natin yung trapezoid sa nakikita nyong ganun ngayon, no? Hidden line. Tapos i-combine natin yung triangle from the left and the triangle from the right. Tapos magiging parang yung triangle sa baba. Yan ang itsura niya. Na 4:3 yung slope niya, 4 vertical, 3 horizontal. So yun, kunin nyo muna yung tangent theta with the use of the slope. Pwede yan. So tangent theta over 2, malamang yung kalahati, di ba, ng theta natin. Since I defined theta as the whole and entirety of the angle if they are added together, no? So, hatiin ko to sa gitna, malamang tangent theta over 2 yan. So, in order for me to get the value of this theta, I will equate it with the slope given to us. And that would give us a value of theta of 73.74 degrees. Then after nyan, kailangan kasi guys yung theta nung dalawang gamitin natin for the Q triangular. After that, yan na. Kunin natin yung Q flow rate ng rectangular, i-add lang natin siya sa Q flow rate ng triangular. That will be the final flow rate. So, ito na yung equations natin. Ang C natin ay 0.75. So, ito yun. Times yung G natin na ito. Okay. L, H. Okay, simple lang naman yan. Direct substitution lahat yan. Para rin dito sa triangular, direct substitution lang din. Take note, same sila ng C value, no? C constant. Pero dito, under tangent theta over 2, ang gagamiting theta ay yung kabuuan, no? So, ang lagay nyo dito ay 73.74 na theta divided by 2. Sana, yan na yung flow rate natin finally as 2.30. And that ends yung Weirs. No? So, more examples of Weirs nandun naman sa ganun natin, no? LMS natin. You can try to read them. I just show you different ganun, no? Examples of different situations. What if rectangular yung given? What if may contraction? What if triangular? What if trapezoidal? So, sir, meron pa bang ibang shape maliban dito sa mga to? Not so much, guys. Ang pangit ng ganun, no, ng open channel na irregular. Actually, kahit irregular nga yung tsura, meron pa rin nasasabi mong open channel sila. Pero, take note guys, ang channel is something that is made by us. May mga natural channels tayo, pero we design channels in order for us to fully, fully use its capabilities. Kaya hindi tayo nag-irregular. More likely, we should use a certain geometrical shape for us to intently do something. So most of the canals, isipin nyo na lang, bakit ang kanal ginagamit nating rectangular? Bakit hindi tayo nagta-triangular? Bakit hindi siya trapezoidal? Tama? Bakit dun sa mga irrigation systems na nakikita natin malapit sa mga palayan, may iba gumagamit ng rectangular? Wala po nakikita ng triangular actually. May nakikita na akong trapezoidal. Ewan ko kung for irrigation purposes yun, pero may mga napuntahan ako na ang canals nila is ganun eh. Hindi naman yung kanal na gano'n na daluyan ng mga ebbs nila, no? But rather, that's a conveyance of water from agricultural purposes. No? May mga gumagamit ng trapezoidal. So, yun na nga, hindi siya basta-bastang nagagano, no? Nilalagay lang yung shape as gano'n, no? Meron tayong pinag-aaralan about dyan at sadya, no? Pasadya yung mga shapes na nilalagay natin. Okay? So, I think that's all for today na lesson. Baka nga bukas, ano ba ang final topic? Ang final topic natin, orifice. I'm not sure if bukas, kailangan pa natin mag-meet. Or baka bukas, ibibigay ko na sa inyo yung problem set. Okay? So, that's it. Thank you guys for listening. Sa lab, pwede nyo nang ituloy yung mga activities na ibibigay nyo sa akin, no? Hindi ka rin kasi talaga ako maka-video sa school eh. Yung hydraulic jump nga, di ba? In my opinion guys, kung sakali, di ba yung sa may laboratory sa school, kung kukuha lang din naman pala ako ng video, no? Di ba, mas magandang yung mga video na lang na pinakita ko sa inyo sa YouTube, yung panoorin. May explanations pa sila dun. Okay, so thank you guys. Till next time, sana may natutunan kayo ngayong araw. So, bottom line ng ganun ngayon na guys, take note of all these formulas and on why it's being used. Kasi, alam ko naman, no, within this time, we mostly likely ang nangyayari, we want to pass rather than try to understand some of the concepts here. Pero, sige, as much as possible, if you can, find out the, ano ba yan, yung, you can find out if the topics are really good for your future, then better for you to understand them rather than just memorize them. No? So, next time ulit na discussions. Thank you guys. Peace out.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye, sir. Tapos,
Thank you, sir.